I already told you total current density in a semiconductor is because of drift and diffusion. Just now we have derived the drift conductivity. Because of drift we have derived NIE sigma is equal to NIE into mu n plus mu p. Okay, what is the role of diffusion? We will see now. Due to non-uniform carrier concentration in a semiconductor, because in an extrinsic semiconductor, either N-type or it can be a P-type, depending on the charge carrier, type, P-type or N-type. Depending on that, extrinsic semiconductor, because of non-uniform carrier concentration in a semiconductor, the charge carriers move from a region, okay, the charge carriers, electrons and holes, they can move from a region of higher concentration to a region of lower concentration, right? So, higher concentration region, if holes are more, then they move to region of lower concentration. So, this process is known as diffusion of charge carriers. Diffusion means migration of electrons or holes from higher concentration place to another lower concentration region. Let delta n be the excess electron concentration. Let delta n be the excess electron concentration. Then according to Fick's law, the rate of diffusion of electrons, according to Fick's law, the rate of diffusion of electrons is proportional to minus dou by dou x of delta n. Delta n is the excess electron concentration. Okay. So, dn is diffusion coefficient of excess electrons. Okay. The diffusion current density due to electrons is given by Jn diffusion is equal to minus E into minus dn dou by dou x of delta n. Okay. That is equal to E dn into dou by dou x of delta n. The diffusion current density due to holes Jp diffusion is equal to plus E into minus dp dou by dou x of delta p. Wherever E this n is there you have to replace it with p for holes. Same equation only, sign change will be there because electron minus E, for hole it is plus E. Okay, current density, diffusion current density due to holes is defined as Jp diffusion is equal to plus E into minus dp dou by dou x of delta p. Okay, then that becomes minus E dp dou by dou x of delta p. The total current density due to electrons is the sum of current densities due to drift and diffusion of electrons. So, Jn is equal to Jn drift plus Jn diffusion. So, Jn diffusion, just now we have derived. Okay, we have derived, of course, for electrons as well as holes separately. Jn is equal to Ne mu Ne for drift plus for diffusion Jn is what is this? E dn dou by dou x of delta n. Similarly, Jp total current density because of holes is equal to drift current density plus diffusion current density. Drift current density for holes is actually Pe mu Pe minus diffusion current density. What is that? Minus EdP dou by dou x of delta P. We got separately for holes and then for holes and electrons separately because of drift and diffusion. Total current density in a semiconductor is because of drift and diffusion phenomena. So for drift, we got a relation for holes. For diffusion, we got relation for electrons. So both together, if you club, you get total current density for holes and electrons. You can see how graph is actually moving. Carrier diffusion, if you take on x-axis and excess electron density on y-axis, you can see the graph how it is going. Now we'll see Einstein's relation. The relation between mobility mu and diffusion coefficient d of charge carriers in a semiconductor is known as Einstein's relation. the relation between mu and D. What is D? Diffusion coefficient. Mu, mobility of charge carriers in a semiconductor. So the relation between these two, mu and D, is actually known as Einstein's relation. At equilibrium with no applied electric field, if the charge distribution is uniform, there is no net current flow. Okay. Any disturbance in equilibrium state leads to diffusion of charge carriers, resulting in a diffusion current which creates an internal electric field. This field causes the drifting of charge carriers, resulting in a drift current. At equilibrium condition, the drift and diffusion current balance each other. Okay, any disturbance in the equilibrium creates diffusion. Okay, they move from higher concentration region to lower concentration region. That is called actually diffusion. What is drift? They are forced to move in one particular direction under the influence of electric field. That is called drift. Drift and diffusion, these two are actually responsible for the current conduction in a semiconductor. So, what will happen? At equilibrium condition, the drift current and diffusion current balance each other. Let delta n be the excess electron concentration of a semiconductor. Then at equilibrium, the drift and diffusion current densities due to excess electrons are equal. That is, delta n E mu n E is equal to, simply instead of writing N E mu n E, we are writing delta n. Delta represents excess electron concentration. Delta n E mu n E is equal to E dn dou by dou x of delta n. The force on excess electrons restoring equilibrium is equal to the product of excess charge and electric field. F is equal to delta n into EE. From this equation, you can write F is equal to delta n into EE. What you can write? This entire equation by mu n. Same thing you wrote. Okay, E dn dou by dou x of delta n by mu n. From kinetic energy, from kinetic theory of gases, the force on gas molecules. Here, these charge carriers act like gas molecules. Okay. So, these charge carriers is given by kinetic theory of gases. According to this, the force on the gas molecules is given by F is equal to kBT. Kb is Boltzmann constant, T is temperature. kBT dou by dou x of delta n. Comparing the equation 1 and 2, what we get? kBT is equal to E dn by mu n. Then dn is equal to mu n kBT by E. Then dn by mu n is equal to kBT by E. dn by mu n is equal to kBT by E. I already told you Einstein's relation is between mobility of the charge carriers and diffusion coefficient. Okay. So, dn by mu n is equal to kBT by E. Similarly, for holes, dP by mu P is equal to kBT by E. So, if you equate right hand side, it is equal. Then left hand side, you make it equal then. dn by mu n is equal to dP by mu P. This relation is known as Einstein's relation. Okay. Equation of continuity, we'll see this is another topic. The equation governing the behavior of charge carriers in a semiconductor is known as equation of continuity. This is something important. Behavior of charge carriers in semiconductor. This equation gives the condition of dynamic equilibrium for the density of charge carriers in any elementary volume of a semiconductor. This is based on the fact that charge can neither be created nor destroyed. The charge concentration in a semiconductor is a function of both time and distance. Okay, conservation of charges means that is charge can be neither created nor destroyed. That you all know since your intermediate itself. The sign difference between the above two equations, electrons and holes, is due to the different directions of drift of holes and electrons in an applied field. You know, sign difference, why it is happening here? For electrons, negative sign, and then holes, it is positive sign. That means if electrons move in positive x direction, holes will move in negative x direction. That is what it means. Consider a unit area of volume element. This is volume element. You see, unit area you consider in YZ plane. Okay, here you see X, Y, Z. These three are perpendicular to each other. They are actually, of course, perpendicular. Okay, and length dx along x-axis as shown in the figure. So, charge carriers entering and leaving the volume element of semiconductor. Here, IP and JP are,